Good morning, dear students. Welcome to another session of Verilog HDL. So in previous session, we started with the discussion of data flow modeling as to what is meant by data flow modeling, how it is different from the previous this thing what we discussed, that is gate level modeling. So data flow modeling is a little bit higher version as compared to the gate level modeling. And it is much more easier to deal with the data flow modeling as compared to gate level modeling when the circuitry becomes more and more complex. So in this one, we checked out the assignments, how the assignments are being done. So in that, we had discussed regarding continuous assignments, then implicit assignments, and net net delay assignments. Implicit continuous assignments. So these are the things what we had discussed. So next we discussed concepts related to the delays. So in delays, the regular assignment delay, then implicit assignment delay, and another one was the net declaration delay. So these all depend on where the delay is specified or at what time. So these all things we have discussed in the previous session. So moving forth, we'll be discussing regarding expression, operators, and operands. So what is basically expression? Expression contains the operators and the operands together so that you'll be getting some results. For example, you want to perform addition. So in that, plus is the operator, and say operands can be the A and B parameters what you have declared. So A plus B will give you the expression, and the intended result is the sum of those two parameters. So expressions are the constructs which basically use the operators and operands in order to obtain certain results. So just few examples are specified over here. So this is A XOR B. The caret symbol which is there, it is XORing operation. Then we have ADDR 20 is to 17 and address to 20 is to 17. You are adding these two address bits which are present over there, and this is the ORing operation you have. So we'll be discussing regarding the operators in depth again. So before that, what is meant by the operands? So operands are nothing but they are the different data types which we have defined or discussed previously. The data types can be of say they can be constants, they can be integers, real numbers, nets, that is net data types, registers, time, bit select, that is if you have a vector, and if out of that if you want to operate only on one bit or multiple bit. So in this case bit select is, it is one bit vector. Or else if you want to use specific part, you can go for selected part of the vector. It can be either of net type or register type. So then we have memories and function calls. So these all fall into the category of the operands. So operands in another form we can just specify in together with the operators. It helps us to get the expressions is intended. Now here, if we just check out, we have integer, which is count and final count. So what is final count equal to? It is given as count plus 1. So here what we have, count is an operand which is of integer type. Even final count is an operand which is of integer type. So similarly, we can have operands of different types. So here we have operands which are of real type, that is A, B, C are operands of real type. So in this expression, A and B are the operands which are of real type, which is providing the subtraction result and storing it in the variable C. So in this way, again, you can see that here reg data type Since we are specifying it to be more than one bit, it is vector in its form. It is not scalar, it is vector representation. So reg1 and reg2 are vectors which are of 16 bits. So similarly we have another one which is of 4 bits, that is reg out. So here reg out is given to be XORing operation of these two, reg1 and reg2. And here you can see that reg1 and reg2 are how much? They are 16 bits. Register 1 and register 2 are 16 bits. Out of that, what you are doing is you are using just 4 bits. Just 4 bits. So that is you are just selecting a certain part of the registers over here. So this is a register data type. You are selecting just certain part of that data. So here you have reg return value. So here, since nothing is specified, this is scalar. So this is 1 bit in its length. So here you calculate the parity. So here calculate parity is a function which is operating on these two parameters. Okay. So this is related to expressions and operands. So expressions include operators and operands, and using these two they obtain certain results. For example, addition, subtraction, adding. So whatever operations are there, those will be performed with the help of the operators and the operands. So operands can be of any data types what we have discussed. So constants, integers, real numbers. So all these things can form the operands. So one special things which come over here is the function calls. So that is an example they have given as calculate underscore parity. So this is a function and this is a function type operand. So it should be say returning some value and that value will be stored in this return value. Now coming down to the main aspect, that is the operators. What are the different types of operators which are present in Verilog HDL? So similarly, you have studied say a microcontroller or microprocessor. So there also you come across these terms like operators, wherein you perform say addition. Addition is a plus is a operator. Then you perform say logical operation. So like say ANDing or ORing, XORing operations. Then you perform some shifting operations. So all these things also should be made available in Verilog because you are simulating or mimicking the hardware in its software aspects. So all these things should be available even in the Verilog HDL. So just a few examples. This is ANDing operation. This is negation. That is only one bit you are negating. This is the shifting operation which is being done. So here this double angle bracket, open angle bracket is an operator. Here this exclamatory mark is a operator. Here the double ampersands which are present are the is the operator. So we'll discuss regarding these now. What are the different operator types? So operator types can be of arithmetic, logical, relational, equality based, then bitwise operators. So up to this point, these are commonly heard. But next one is the reduction operator. So this is one new thing which comes over there. So reduction is one special operator what we'll be checking out. Then even in equality, we have some special cases over here. So those also we'll be checking out. We have shift, then concatenation and conditional. So operator types can fall in these categories. Operators can fall in these categories. So arithmetic, logical, relational, equality, bitwise, reduction, then shift, concatenation, and conditional. So we'll discuss a few of them over here and what are their symbolic representations. So first we have the operator types. In this we have arithmetic operators. So in arithmetic operators we can have multiplication, division, addition, subtraction and modulus operation. So these are the different operations what we can perform. So what is the symbolic representation of these? So asterisk or star represents multiplication. Then say the front slash represents the division, plus symbol represents the addition, minus symbol represents the subtraction, and percentage symbol represents the modulus. And how many operands are required for these cases? I require 2 operands for each of these arithmetic operations. So if I just classify it, it is what kind of operator? It is a binary operator. It is a binary operator. So you have 3 kind of operators. One is called as unary operator. So in this one, the operand is only one. Next one you have binary operator. Binary operator requires 2 operands, and last one you have ternary operators. So ternary operators require 3 operands. 3 operands. So unary operator requires 1 operand and 1 operator. Binary this thing requires 2 operands and 1 operator. Ternary requires 3 operands, and if we look at the operation, it requires 2 operators. 2 operators. Okay. So this is arithmetic operation. So here one thing to so these all are okay. That is multiply, division, addition, and subtraction. The one thing what we have to check out is modulus. So in modulus, what happens is it returns the remainder part. It returns the remainder part. So if I am say estimating something in the form 7 mod 4. So here what we do is we divide 7 by 4 and see what is the remainder. So in this case, the remainder will be 3. Remainder will be 3. When we are doing the division operation, I'll be getting the quotient part. I'll be getting the quotient part. When we use this percentage symbol, right, that is a modulus operator, we will be getting the remainder part. So this is related to the arithmetic operators. Then coming down to logical operator. So we have logical negation, then ANDing, and ORing operations which can be performed. So here, we can see that say the exclamatory mark what we have represents the negation. Double ampersand represents the logical ANDing, and double broken pipes represent the logical ORing. Now here one thing to note down is logical negation requires only one operand. It requires only one operand. So since it requires one operand, this is a unary operator. This is a unary operator. Whereas logical ANDing and ORing requires 2 operators. So these 2 are binary operators. Now coming down to the relational operators. So relational in the sense again greater than, less than, greater than or equal to, and less than or equal to. So these are the operations which have to be performed. And these are the symbols which represent each one respectively. So open angle, closed angle bracket, open angle with equal to sign, and closed angle with equal to sign. So these represent greater than, less than, greater than or equal to, and less than or equal to respectively. And for these operators, you require 2 operands each. So because of which these operands, I can term them as binary operators. So next we have equality operators. Equality operators. So we have equality and inequality, then case equality and case inequality. So let us look at these things. So first one is double equal to and negation sign with the equal to. So these 2 operators provide you the information whether the two operands are equal or whether they are unequal. So this requires two operands. So therefore, these two are again binary operators. Now, when we look at the other part, here you can see that you have three equal to signs. Three equal to signs, and in this one you have a negation and a two equal to signs. So this, if I use such this operator, right, it specifies regarding case equality or case inequality. Now, when does this come into picture is now in previous this thing we had studied, right? Say you have binary numbers. You have binary numbers. Okay. I'll just specify. I have four bits, and it is binary in its representation. So 0, 1, 1, 0. So this is the number. 0, 1, 1, 0 is the number. Now if I have another four bits number, and so I have something like this. So if I use say if it is A and this is B, if I want to test that, if I want to perform some operation, whether both are equal to or not. So here if A is equal to B, then perform some operation, else perform some other operation. Or else you can write it in the other way. If A not equal to B, then perform some operation or else leave it off. Now what will happen? What will happen? What will happen when you have something as say X specified over here? Because this is possible. You can specify a value as unambiguous or ambiguous. You can specify it as X or Z. So even this is possible. So in this case, what happens is if you use either this operation or this operation, what happens is so 0, 1, 1, 0. So 0 is matching, 1 is matching, and the last bit is matching, but this bit is not matching. This bit is not matching. So in this case, what happens is logically the result is both the numbers are not equal. Both the numbers are not equal. So that is the logical representation what we follow. But I want a condition wherein I want to check bit by bit and see whether they are matching in each and every condition. So in these cases, right, what happens is you'll be considering zeros and ones. But if X comes, then it creates a problem. X comes, then it creates a problem. So the logical aspect fails over there. Suppose I have a number as 0, 1, x 0, say which is stored in A, and in B I have another number 0, 1, x 0. Now if I want to compare numbers when they have X and Z values in them, say I'll take this as Z, take this as Z. I want to compare numbers which have X and Z values in them. If I use this case equality and case inequality, there it will be failing because it will be checking only for zeros and ones. If some term comes over there, then it will fail to provide the result. It will tell that they are not equal, or the result will be unknown. The result will be unknown. But in such cases, I want to see that even whether there are numbers which are similar in each of the bits. So in this case, zero and say in such cases, I want to check out whether both are equal bit by bit case. So in that this thing, I go for this case inequality statements. Case inequality. These are just equality and inequality. These are case-based inequalities or equalities. So here what we do is, so we check the first bit, both are same. We check the next bit, both are same. So when we come here, it is X. Whether here also it is X, it will check. Then here it will check. So in our case, it is Z. It will check whether it is Z over here. So if all match, then it will give you a logical one. That is true condition. But in this case, right, that is not possible. That is not possible. So it will check for only 0 and 1. If some other term comes in, that time it fails off. So in this one, what we are doing, we are checking for each and every bit. 0 is there, 0 is there, 1 is there, 1 is there, x is there, x is there, z is there, z is there. So what you're doing is you are checking it bit by bit. So whether each bit is having same representation. So that is one special feature of case inequality and case inequality. So this is what we have to check out for. So next we have bitwise. So here bitwise, so it is tilde operator, then ampersand, then broken pipe, then a caret. So this is caret is actually XOR. So if I want XNOR, I take a caret operator and put negation, or take negation and then put caret operator. So it provides you the XNOR operation. Now here to remember the stuff is it is bitwise operation. Whereas here you could see that this is logical operation. This is logical operation. So this is bitwise operation what you are performing. So you are negating the bits in bitwise form. This is logical negation. This is logical negation. So we'll come back to that point again. So here we have doing bitwise and bitwise or bitwise XOR and bitwise XNOR. So here a negation, you can see that it requires just one operand. So since it requires just one operand, what does this imply? This is a unary operator. And others, if you just see, you require two operands. So which specifies that these are binary operators. So we'll discuss regarding the difference between bitwise and logical operators. We'll discuss regarding that in coming forth, say session or in this session itself. So just remember here you can see that double ampersand, double broken pipe, but here you have single ampersand and single broken pipe. So caret operator which is present. So this is bitwise operation. This is bitwise operation. So next again reduction. So in reduction again ampersand, that is reduction NAND. Then tilde followed with the ampersand gives you the reduction NAND. This is OR. This is NOR operation reduction. Again this is reduction XOR. Then this is XNOR. So this will discuss with respect to the examples. So here you can see that all these require only one operand. So these are all unary operators. These are all unary operators. So next you have shifting operation, that is say right shift and left shift. So this requires two operands. So this is a binary operator. So one special this thing which is present is concatenation, or sometimes called as replication. So this is concatenation. So in one of the examples we had discussed regarding this part, but not in depth. So here with an example, we'll check out how concatenation is actually performed. So concatenation, only concatenation is there, then it is specified within the double braces. So how it is specified, we'll check out in the examples. So any numbers can be concatenated. Now another thing is I want to have a replication of a certain number. Say I want to replicate number 4. Say I want to replicate it 10 times. Or I want to replicate a variable, say parameter which is declared as a real value, say real number 1. So I want to replicate that say 10 times. So I'll be providing that information in this form. So we'll check out this also in with an example. So here again, any number of operands can be utilized. Or the last one which is there is conditional. So the operator for this one is question mark with a colon. Now here it requires three operands. So this is the only operator what we have seen up to now which requires three operands. So this one is another one which requires which can take any number of operands. So this one is called as ternary operator. So this operator is termed as ternary operator. So we have the arithmetic operators. So we'll come across the binary operators. Binary operators are multiply, divide, add, and subtract, and the modulus operator. So they basically take two operands. So that is what we discussed in above table. So here we have just taken few examples. A is a 4-bit number which is binary and its value is 0011. Similarly, B is also defined in the same way. So here, since it is not just 1 bit, it is more than 1 bit, it is register vector data type. It is register data type which is in the vector form. So here we have D which is equal to 6 and E which is equal to 4. So these two are integer data types. So now here A star B will give you the results of the multiplication. So when you multiply these two, you'll be getting this result. So if you want, you can just perform the operation and see whether you're getting this result. Similarly, D divided by A, that is 6 by 4, it will provide you the result quotient, that is it is equal to 1. So any other fractional part which is there, it will be truncating that part. So fractional part is nothing but the remainder what is present. So if I want to get the remainder, I can use the modulo operator. If I want to know what is the remaining part, you can use the modulus operator. So this is A plus B, which will be adding the two parameters, B minus A, which will be subtracting the two operands which are present over there. So these are your arithmetic operations. Now here, some special conditions what we have to check out is, what if the operand bit value is X? So here we can see that in 1, it's a 4-bit binary number whose value is 1101X. So here we are having a X. So what happens to the overall result when we perform the arithmetic operations? So here these in1 and in2 are added together. So since there is a X present over here, that is ambiguous value, then what would happen is the result would be entirely X. That is, the expression entirely would be evaluated to X. That is, sum will be equal to 4 bits. It will be 4 bits binary and its value will be unknown. That is X value. So this is one special thing what we have to note down when we come across with these kind of numbers. Then here we have modulus operator in which the remainder is being utilized. It is division of two numbers, which gives you the remainder part. So here modulus operator basically returns a remainder. So here we can see few examples. What is the remainder when you divide 13 by 3? So it is 3 4s are 12 and 1 remains. So remainder will be 1. So similarly here you can see that minus 7 divided by 2, the remainder will be minus 1. So, so here what we are seeing is the sign what is taken is dependent on the first operand. Sign which is taken, it is dependent on the first operand, because here we can see that the second this thing 7 divided by minus 2. As per our this thing it will be minus, but in this case what happens is the remainder will be plus 1 because the first operand's sign is plus. So in this case the first operand's sign will be considered. So you have unary operators which are plus and minus. So they are also used in addition and subtraction, but they can also be used in providing the sign aspects of the operands. So here plus and minus can also be used as a unary operator. Now here we can see that minus 4 and plus 5. So this is negative number, this is representing positive number. But we should be careful when we are using it in operations. Say for example here you can see that it is minus 10 divided by 5. When we are performing this evaluates to minus 2. So this is not a problem. This is not a problem when we are dealing with integer or real numbers. But if you are representing the numbers in binary or any other stuff, right, then you should be careful, because what happens is if you're using it with this specification, that is you are providing what is its sign, then you're providing what is its base representation, and then the number. So if you're using it in this form, be careful. Why? Because operation will be performed in a proper form, but the representation will be different. So when you're using this approach, instead of just specifying minus 10 divided by 5, instead of this, if I specify it as minus, this is unsized number. This is an unsized number. If you remember, if size is provided, it is size number. For example, here, right, 4. So it tells that the size is 4. So this is a size number. If this number was not present, then it would be unsized number. So here we have minus, then it's a decimal number 10. So when we represent the data in this form and we use it in the arithmetic operation, what happens is, uh, as the operation is performed in this one, it will not be performed in the similar fashion. What it will be doing is, first it will be converting this part, that is minus D10 to 2's equivalent. And then it will be performing the overall operation and the result will be in 2's complement form. So again, you should be careful when you are using this kind of approach. So generally it is advisable to go for this representation instead of this representation in an expression. Okay. But even then, if you're using it, then be careful in, say, analyzing that result. Okay. So here he is assumed that the system is 32 bits. Therefore, he is representing it as 2 raised to 32 minus 10 divided by 5, which is the 2's complement form of minus 10. So here, because of this, you might think that the results are unexpected. So all these things are possible. So when you perform this operation, right, the remainder might not be equal to 2. So it might be more than 2 also, or less than 2. So we cannot specify. So be careful when you are performing such operations using this representation. This representation. So next one we have the logical operators. So logical operators, double ampersand, double broken pipes, and a negation sign. So this is logical and, or, and not. Okay. So these two are binary operators, whereas this is the unary operator. So now, so here what we have to look out is logical operators always evaluate to 1 bit value. 1 bit value. So it will be either true or it will be either false. And another state, it can be in ambiguous form. So why ambiguous? If say in the binary number x comes over there, then in that case it will be ambiguous whether to go for true or false. It will be ambiguous. But in general, what happens is it is considered as a false condition. In a logical aspect, it is considered as a false condition. So here, if an operand is not equal to 0, it is equivalent to logical one, that is true condition. And if it is equal to 0, then it is equivalent to logical 0, that is the false condition. So we'll check out these things in these aspects, that is examples. So here one thing to remember is, if any operand bit is x or z, then the entire expression evaluates to x, that is ambiguous condition. And this is actually treated as a false condition in your simulation. So logically we treat it as false condition. Logical operators take variables and expressions as operands. So let us see what actually happens in this case. So first thing to remember is, it just gives you 1 bit value, either 0, 1, or x. So these are the 3 possible values which you have. Okay. So here I have a is equal to 3 and b is equal to 0. So when I perform a and b, so it is like it should give me 1 bit result. So here, if I represent it in binary, what I'll be having 1 1 and 0 0. So when I add this, what I'll be having 0 0. So it is, so here this will end up in what? This will end up in 1 bit value, that is 0. This will end up with 1 bit value, that is 0. So what is this actually equivalent to? What is this equivalent to? So it is equivalent to logical 1 ANDed with logical 0. So this is a non-zero value, this is a 0 value. This is a non-zero value, this is a 0 value. So what is this operation performing? It is checking whether both are 0 or both are non-zero. or both are 1. So it is checking. If both are 1, then only the result will be 1. If any one of them is 0, it will evaluate to 0. Okay. So here that is what this second part implies. If an operand is not equal to 0, it is equivalent to logical 1. If the operand is equal to 0, it is equivalent to logical 0. So if any one of the operand is 0, the result will be 0. If both the operands are non-zero, then the result will be 1. That is logical 1. Then we have ORing operation. So in ORing operation, what we have, if any of the operands is non-zero, then it will evaluate to 1. So here what it is happening, A is a non-zero value, that is it is like logical 1. B is a 0 value, it is like logical 0. So when you XOR 1 with 0, what you'll be getting? We'll be getting 1. So in simple form, if any one of these operands is 1, this ORing operation will result in a logical 1 value, that is true condition. So next we have negation of A. So in this negation, what happens is if the number is 0, it will be evaluated, its result will be logical logical 1, and if the number is not 0, then its result will be logical 0. So here A is equal to 3, A is not A is equal to 3, it implies that A is a non-zero value. A is a non-zero value. So when I negate this, what happens is it turns out to be 0. That is, this is like a logical 1. That is what we are specifying. If it is non-zero, it is logical 1. If it is 0, it is logical 0. If the number is non-zero, it's a logical 0. Similarly, if you just see B, negate B, what is B value? B is 0. So since it is a 0 number, it is logical 0. Since A is a non-zero value, it is logical 1. So if you negate these two, you'll be getting the opposite result. So logical 0's opposite will be logical 1. So this is how the logical operators perform. So we can observe that logical operators provide only one bit result. They check whether the number is non-zero or not. If the number is 0, it is equivalent to logical 0. If the number is non-zero, it is equivalent to logical 1. So this is how you have to perform the operation. So now what happens when we have X or Z values? So now here we have 2 bits in binary form, 0 and X, and here we have 1 and 0. So when we perform the operation over here, what happens is, so this one is unknown, so its logical representation will be X. Its logical representation will be X, and this one is a non-zero value, so this is equivalent to logical 1. So this one, the expression again evaluates to what? It evaluates to X, that is ambiguous value. It is like X, that is X value ANDed with the logical 1. So the result will be unknown. So here in terms of expressions, if we look, if A is equal to 2 and B is equal to 3. So you are looking in this form. So you're checking whether this is true or whether these two are true. If both are true, then only you will be provided with the logic 1, or else you will be provided with the logic 0. Okay. So it is like both the conditions have to be satisfied. So because since it is an AND condition, both should be 1, then only you will be evaluating it to logical 1, or else you will be evaluating it to logical 0. So remember, logical operations result in 1 bit value. 1 bit value, the values can be either 0, which is false, 1, which is true, and X, which is ambiguous. But generally, X is considered as a false condition in simulation. So if you are using that value over there in, say, if statement something, then it will be like if X comes over there, it is the false condition which is present. So another thing to remember is if the number is a 0 value, it is equivalent to logical 0, and if it is a non-zero value, it is logically equivalent to logical 1. So next we have the relational operators. So relational operators, again we have greater than, less than, greater than or equal to, and less than or equal to. Since all these require two operands, right? These are all binary operators. Now here again, in this case, we have to just check out. So if there are unknown, that is x or z bits in the operands, then what happens? The overall expression again evaluates to x. Evaluates to x. So let us just check these things. So we have a is equal to 4 and b is equal to 3. So what we are doing, whether a is less than or equal to b, whether yes or not, whether true or false. So 4 is less than 3 or not, no. So this is false. So this will evaluate to logic 0. Whether a is greater than b, 4 is greater than b, that is true, it will evaluate to logic 1. Now here we have other condition. What if x or z is present in the numbers? X or z is present. So here we can see it is 1010 and 1101 in binary form. So checking whether y is greater than or equal to x. So 1101 is actually greater than 1010. Therefore, it evaluates to logic 1. Now, when you consider for the other one, whether y is less than z. Now here, since in z, right, you have x values present. So this expression will evaluate to the ambiguous value, that is x. So this is what happens in this case, that is relational operators. This is what is happening in relational operators. So next one is equality operators. So in equality operators, you have logical equality, logical inequality, and case equality and case inequality. So let us look at the expressions. What are the possible logical aspects related to this? So first one, double equal to, which is what? Logical equality. So here what we are doing, whether A is equal to B. So in each bit, it will be matching. It has to match. Now in this case, what happens is if any of the bit is either X or 0, if any of the bit in either of these is X or Z, it is X or Z, then the expression evaluates to X, that is ambiguous parameter. So it should be matching in terms of zeros and ones. If any of those bits is either X or Z, then the whole expression, that is this expression, will be evaluating to X. So similarly for A not equal to B, if A is not equal to B, then it will be giving a logical 1. If A is equal to B, then this will be giving you logical 0 value. But if any of these bits or any of the bits in A or B or in both, it is either X or Z, then this expression will be evaluated to ambiguous value. So therefore, the possible logical values in the logical inequality and the logical equality are either it is false, either it is true or ambiguous, false, true or ambiguous. Now coming down to the other aspect, that is case inequality. Case equality and case inequality. Whether A and B are matching in each of the bits, including X and Z. Including X and Z. So here whether A and B are not matching in terms of the zeros, ones, and including X and Z. So in this case, what happens is it will be either true or false. It cannot be the other expression. This expression cannot be evaluated to the X value. This expression cannot be evaluated to X value. So that is, we can just check out an example over here. A and B. So here 4 and 3. So whether A is equal to B, 4 is equal to B, no. So this will evaluate to 0. Whether X is not equal to Y. So here we can just check out. X is 1 0 1 0 and Y is 1 1 0 1. So here both are not equal. So this one will result in logical 1. Now here we have X as 1 0 1 0 and Z as 1 X X and Z. So I am checking with logical equality. Now since there are X and Z values, it can be only X or only Z values also possible. So if I have these values, then the expression evaluates to ambiguous parameter, ambiguous value. So similarly in these two, similarly in Z and M. So here you can see that I am using what three equal to signs. So this is case inequality. So here you can see that first bit is same as the first bit of M, X, next bit is M, X, here also it is X, here also it is X, then Z and Z. So they are matching case by case. So each bit is matching. So in this case, what happens? It will evaluate to logical 1. If this was X, instead of Z, if this was X, then there would be a mismatch and this would be false. So that is he has taken in the next example. So here we can see that first bit is matching, then next bit is matching, which is X value, next bit is matching, which is X value, but last bit, if you just see, this is Z and this is X. So here what it implies, case inequality when we are doing, since the last bit is not matching, this will be evaluated to logic 0. So similarly, we can go ahead with the last one. So this is the difference between your logical inequality and equality and case inequality and equality.